This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so I got it drawn neatly. So your input signal got, so your frequency of interest is 20 megahertz. So that is your frequency of interest in a particular signal, input signal. Your frequency of interest is 20 megahertz. But then when you take FFT of your input signal, you found out 20 megahertz is there. Yes, your signal of interest is there. But then you also got some 30 megahertz, 40 megahertz, 50 megahertz, 60 megahertz, 80, 100. And then these are the FFT. So these are the sinusoidal signals, different sinusoidal signals. So when we can represent here, so this is a frequency, so that is a frequency, and then this is the amplitude. And then we will be using an ADC 60 mega samples per second. So 60 megahertz, that is a clock frequency in the ADC. So this is your ADC, and then here this is a 60 megahertz clock, and then this is your input. So input is X. So that's the input is going. So if you are putting this input, as I said, the ADC will be using 60 megahertz, and then you may see only this input signal, kind of a triangular. Then you might be thinking, where are those high frequency components? So high frequency components are when you take FFT, there are so many sinusoidal signals. This will be there, and then each signal will be sampled with respect to the clock. So that's how your error. Otherwise, you may think that no, my signal, that is kind of a triangular signal. I don't find any other frequencies. But then when you take FFT, so you will be seeing so many sinusoidal signals. And then each sinusoidal signal will be sampled by the ADC clock. And then here the ADC clock frequency equal to 60 megahertz. And then even you got 60 megahertz in your signal. Then 60 megahertz will come. When it is sampling, it will be a straight line. There is no frequency. So that will appear here. You don't have much issue with that one. But then when you have 30 megahertz, it will be how much, where it will come, you can easily find out. Your sampling frequency, Fs, that is equal to 60 minus, this is the frequency of interest 30. So that will be folding back to, so that is the reason aliasing. So it will come here. And then your 40, the 40 is another problem. 40 will come exactly here, 20. But then 50, your 50 is a problematic one. 50 will be sampled as 60 minus 50. That will appear as a 10 megahertz. And then, so you want to avoid this scenario. You don't want to connect your input directly to the ADC. If you connect it, you will be getting unwanted 10 megahertz. Then 20 megahertz again, you are getting twice because of your signal and also, because of this one. So then you don't want these things happening. Even Fs by 2, here you are getting unwanted aliased signal. So that's called aliasing. In order to avoid aliasing, what people do is they put a low pass filter. Low pass filter, that is called anti-aliasing. So anti-aliasing means you are avoiding the aliasing. So in this case, you are designing an anti-aliasing, and then your signal of interest is 20 megahertz. Then ideally, you should have, in the ideal world, you can have a band pass filter, low pass filter. So this is a frequency, this is a filter, so this is the response you should be having. So if you got this filter response, this one, then you are fine. Because then you are only passing up to 20 megahertz, and then you are suppressing all the 30, 40, 50, 60, 80, all gone. So this is your stop band starting. So this is your stop band. This is your pass band. So then your X, so all the frequencies, so all these things. So this I say FFT. So all the frequencies 1, 2, 3, 4, 5, 6, 7. 7 frequencies are 7 frequencies, components, frequency components, FC. I'll write 7 frequency components are going, and this anti-aliasing filter here only 20 megahertz, up to 20 megahertz, 0 to 20 megahertz only will go to the ADC. You know what I meant? Because this will stop all the high frequency part. So that is the reason it is called anti-aliasing filter. You know what I meant? So that is the reason before the ADC we need a low pass filter to avoid this aliasing, folding back of high frequency signal in the form of low frequency signal due to the error. But then if you can make a filter something like this, you are lucky. But in the real world you can't get a signal. If you want to make this type of response, you need infinite number of poles or infinite number of order. So what you can do is, in your case, when you design a filter, your filter something, it will be like this. You know what I meant? So your filter response will be something like this. Now my question is, where you will plan your stop band? Because now in the real case, when you design a filter, you got a this is what is called a pass band. Then you got a transition region. Then you got a stop band, because you can't get a straight, top hat. So you will be getting a kind of slope. But then your question is, where will you put this stop band? Which is the frequency you will put as a stop band? Which frequency will create issue in your frequency of interest? Yeah, so if you take 40, because here you got 30. 30 is sampled wrongly, but 30 will appear in 30. If you got 35, see, if you got even a 35, where 35 will come? 35 will come again here. You know what I meant? If anything is there above 40 will come definitely. So above 40, whatever is coming, all these things are coming to this region. You know what I meant? So above 40, so your stop band is then, what is the stop band? That is 40. So that is the reason we call it as your stop band should be Fs minus Fb. So Fs equal to 100 minus 20, sorry, Fs equal to 60 megahertz. So that is Fs minus 20, which is equal to 40. So that is the reason your stop band should be 40 megahertz. So you don't want to have anything from the 40 megahertz, because that will fold back into your frequency of interest. So this is this is your Fs minus Fb. So we don't want anything. And then so this is a Fs by 2, and then this is your frequency of interest Fb. You know what I meant? So that's how you will be designing. So that's the only way we can design. So then in the transition region, what is happening? In the transition region, this frequency will appear here. In the transition, this frequency will appear here. In the transition region, this frequency will appear here. This frequency will appear here. You know what I mean? But amplitude is decreasing, so that's okay. It is attenuating. So this region, whatever is coming here, definitely after the Nyquist rate, after the Nyquist frequency, your errors are coming, but that is coming in this region. It's not folding back to your pass band. But then my question is whether this region is a problematic or not. Whether this region will come into your region or not. So now this is so this filter is LF ideal, ID. So this is a low pass filter ID, ideal filter. So this is a low pass filter real. So in the real, then so your X signal is coming, and then you got a low pass filter real, and then you are connecting to ADC and doing sampling. Then here it is 60 megahertz. So now my question is, here your X got so many frequencies, like 7 frequency components. That's what. So then my question is, here what will happen? So what you will see? Will you get this region in the signal in the region? Yes, because these frequencies will be sampled and folding back to this region. So you are actually getting some error, but then only thing is because this region is, see, this region is amplitude is like this. So that when you have folding, it will be like this. So this is the reflected one. So this will be reflected. You know what I meant? So that it's not a big issue. You are getting this much because here it is attenuated is like this. So that you are getting this one. So this much is actually going into your system little bit, but then it is because this one is exactly reflecting to this region. But anything after this one will come in the frequency of interest because that will be passing without any attenuation. So that's the reason our stop band is 40. After 40, we will not allow anything to go through. So then I don't like this design. Why? Because I am not interested even, this much part is folding to this region. I am not interested. So how can you reduce this region? So means now see from A to B, this region is not our region of interest. But then here also it is sampled wrongly and coming to this region like this. But then I don't want even this much region. Then what you can do is you can make much more sharper. Then you can increase the, what you can increase? You can increase the number of poles. But then when you increase the number of poles, what will happen is you are using extra op amps. Your second order might become sixth order. And another coffee question. Okay. So you can join the other two questions as said, otherwise you have to buy me a coffee. So please awake. You will be in big debt after taking ESD. You may have to borrow a loan to buy me a coffee. So you encountered this issue, but then we don't have enough number of op amps. Or in your system, you can't put in enough op amps because of the power. Power is taking a lot. Then somebody asked can we do something without increasing the order? Because increasing the order is a straightforward way. So I will give you 2 minutes, and then whoever is telling like first 3, I will buy you coffee, but if remaining people have to buy me a coffee. Okay, take 2 minutes. So this issue came up. Like one way of solving, you already discussed it. See, I told you, increase the number of orders, so that's good. But if that is not possible, because you are using extra op amp, extra power, and then area, you need more area, but then somebody will ask you, can we do something other than this? So, okay, so you will get a coffee. So you get 2 coffees. Last time you answered. So it's correct. So I got answer. So anyone else? Anyway, good. Whatever you said is not clear. So other people got opportunity to think. Yep. So we can use an ADC with higher sampling frequency. See, then also you can reduce the error. So when you increase the sampling frequency, what will happen? Now your transition region, what is the width of your transition region? So this is 20, this is 40. So the width of the transition region is 20 megahertz. So that is the width, this width. So if I am using ADC with 120 megahertz sampling, what is the width of the transition region? So if I use a ADC, because we already got the answer, if you use a higher clock frequencies in the ADC, then you can get a much better result. But then instead of 60 megahertz, I am going to use 120 megahertz clock in the ADC. In that case, what is the width of the transition region? Because here width of the transition region is, this is 20 megahertz, and then this is a 40 megahertz, because here is the stop band is starting. So this width is equal to how much? 20 to 40, so 20 megahertz. If you are using 120 megahertz clock, So my question is, what is the width of this transition region? So definitely it is more, because FB, your FB equal to 20 and then Fs minus FB. So Fs equal to 120 megahertz and then minus FB 20 and then that is equal to 100 megahertz. So then your width is going to be much higher. And then when the width is going to be much higher, how will you benefit? Then you might think that, oh no, that is not the case. You should be going other way around. You should not be going other way around, but because here, actually here we assume that we are completely stopping it. Actually we can't completely stop the band. You will be putting a very high attenuation and then you are not completely eliminating it. For example, so this is your magnitude and then this is the frequency. And then here this is your, maybe from here you are starting 0 dB. So this is a 0 dB of your filter. And then you will be having something like this response. Like this. And then this could be minus maybe 40 dB. So that is your stop band. From here your stop band is starting. Because you can never make this 0. You can't, you are attenuating a lot, minus 40 dB. But then, so this is your pass band. And then this is the transition region. So then what will happen is like this, and then so then what will happen is actually you are not attenuating actually here. So here you are not fully attenuating, you are partially attenuating, you are attenuating a lot, but then still it can come to this region a little bit. You know what I meant? So the better drawing is, so I will show you. So what I meant is, so here we are taking an example. So this I have drawn it so that it is clear. So here, this is your frequency of interest, that is 20 megahertz. And then our stop band, where stop band is, sorry, yeah. So where the stop band should come. So then, so this is a anti-aliasing filter. Ideal case is this dotted line. So what I meant is, if you got a 20 megahertz sampling, that is your interest, then immediately you can, somebody will ask you, 20 megahertz is your bandwidth of interest, where should be your stop band? Then you can ask, okay, what is the sampling frequency? Yeah, sampling frequency is some number, Fs. Then you can say stop band should start from Fs minus Fa, which is clear now, because after that it will be aliasing. And then if your sampling frequency is say 100 megahertz, and then your stop band should be 80 megahertz. So when you have your stop band 80 megahertz here, then what is happening is, see, your pass band, then this is the transition region, and then see, in the transition region is coming like this, and then after the transition region, so these are the, here you are attenuating. So this is attenuated. Stop band attenuation is DR. So this DR is maybe this is minus 60 dB or minus 40 dB. You know what I meant? So from here it is attenuating. So the signal is attenuating like this. From here it is attenuating. Then what will happen is your filter profile is like this. And then it is like this. Then what will happen is the filter up to here. See, this part also will be a little bit reflecting here, because here you are attenuating, but then you are not eliminating. So that is the reason this part is folding back a little bit to this region. You know what I meant? So this will not happen if your filter is filter got is coming like this and it is ending here. But then you need a very high order. So that is the reason your filter will be something like this, and then this is your stop band. So from here is the stop band frequency. And then here you can see 20 megahertz is your frequency of interest, and then you are sampling with 80 megahertz, then your stop band should be 80 megahertz. If it is not 80 megahertz, whatever is coming beyond will be folding back to this region of interest. And then this region, see, this width is very, very small, 80 minus 20, so that is equal to 60 megahertz. So in that case, what will happen is you need a very high order filter in order to meet this requirement. You know what I meant? Because this is a very sharp region. But then sharp transition is required and hence more number of poles. This increases the complexity, number of op amps and power requirements. Then what you can do is, in order to avoid this one, you can have a sampling frequency of 200 megahertz. So when you have a sampling frequency of 200 megahertz, what will happen is now you are getting your 120 megahertz. Now your stop band is, you are pushing the stop band. You know what I meant? So you are pushing the stop band. Now your stop band equal to 120 megahertz, because whatever is coming after 120 megahertz only will be folding to this region. So that you can have maybe a second order filter will do your job. So that's what. So when you increase the sampling frequency, what you are doing is you are pushing the stop band. So now I will come back to the drawing. So because I want to make sure that you understood. Now I am coming back here. See, here everybody is agreeing. When you have 60 megahertz, so we are using 60 megahertz clock. So when you have 60 megahertz, yeah, this is the lowest. Yeah. So if clock equal to 60 megahertz, that is a sampling frequency, that is a clock. Case 1. If you have 60 megahertz clock, your frequency of interest is 20, so that is a 20 megahertz. That is the frequency of interest. Then your Fs minus Fb, so Fs minus Fb equal to 40 megahertz. We already got 40 megahertz. So whatever is coming after 40 megahertz stop band, we have to stop at 40 megahertz. If something is coming after 40 megahertz means it will be folding back to this region. Even if you are attenuating 0, that is fine, but it will not be 0, because this part you are attenuating maybe minus 60 dB, something like that. So that little bit anyway it will appear here, because here it is not possible to attenuate completely. And then we cannot allow any signal above 40 megahertz not attenuated fully, means not completely, heavily attenuated. So this signal is heavily attenuated. So your Fs minus Fb, and then Fs minus Fb equal to 40 megahertz. Then what happens is this is 20 megahertz, this is 40 megahertz. So in order to fulfill this requirement, you can have only transition region should be coming down to your this much attenuation in 20 megahertz. See, your 20 megahertz, only you got a sharp transition. You know what I meant? But then in order to get this one, this criteria, what will happen is you may end up having maybe 6th order filter, maybe 10th order filter. Then only you can get in within 20 megahertz, you should get a transition region. Then in order to avoid that one, you can use as ADC with, I will say, 120 megahertz. So option number 2. So when you are using a sampling frequency 120 megahertz, then what will happen is here your Fs minus Fa, that is equal to 40 megahertz. Then here Fs minus Fa, which is equal to 120 minus 20, which is equal to 100 megahertz. Now your new Fs minus Fa, so now in your new filter, what will happen is in your new filter, so this is 20, so that is 20, and then you can have your Fs minus Fa, so this 40, now we can have 100. Because after 100 megahertz only everything will be folding to your region of interest. You know what I meant? You got it? So this is, so in this one, Fs equal to 60 megahertz, then what is the stop band you need is 40 megahertz. So if you don't want to use a, so for this one you need a 10th order, 10 poles. But I don't want to use a 10 poles, I want to use maybe two poles. Then what you need is, what do you need? You need a sharper transition region. You don't need a sharper one. I can't afford a sharper one because I can't have 10 poles. So I'm going to use a second order one. But if I use a second order one, what will happen is it will be like this. Then you are allowing this 40 megahertz to come into this region. You know what I meant? But then, if I can push this to further away, then I can have a less sharp transition region. Or, this is a question, with 60 megahertz, our stop band should start, when you are using a 60 megahertz clock, our stop band should start at 40 megahertz. So if you are using fs equal to 120 megahertz, where should my stop band start? Your frequency of interest is 20 still, but then your clock frequency is now 120. Now where I should start my stop band? Sorry? Yeah, 100. See, now you can have 100 megahertz. See, now you don't have to worry about this small transition region. Now your stop band from 40, now it became 100 megahertz. See? Now when you draw it, what is happening is, so this is 100 megahertz. So now your filter is saying, see, 20 megahertz. But then now you can have a less sharper transition region. So now your pass band is starting from 100 megahertz. So if everything above 100 only will be folding back to this region. See, everything above 100 only will folding back. Previously everything above 40 was folding back like this. See, everything above 100 will be folding back like this. So you are pushing the stop band maximum frequency. You know what I meant? So if you are pushing, then the advantage is you can use a less number of poles to get the same performance. So that's the reason you can increase the sampling frequency. So when you are increasing the sampling frequency, so what is happening is you can afford to have a less number of poles, because now you are, because anyway from here to here it is folding back to this region. Now your 120 megahertz, that is your stop band frequency starting region. Above 120 only will go to this region, so that you can have a less sharp region. So that's the reason we are discussing. So this curve is it will give more insight. So this is your pass band up to the frequency of interest, that is FB, that is equal to 20 megahertz. So this is your sampling frequency, and then this is the frequency, sampling frequency. This is fs by 2, Nyquist frequency. This is the sampling frequency. This is fs minus fb. So fs minus fb will be folding to your frequency of interest. All the frequencies above fs minus fb will be folding to your frequency of interest. So we have to stop this fs minus fb, and then so that is the reason we should have stop band here. But if you are using a high frequency clock, the advantage is you don't need a narrow transition region. You can have a much higher, bit more slope. It is possible. So please think about it and get in touch with me if you have any question. Then in your case, now the question, in your case, what is the signal of interest? What is the bandwidth signal of interest? What is the frequency? Yeah, so I am coming back to your design. So your design is pretty tight. So that is the reason I told you, someone, if you are not worried about your design, you haven't understood your design. In your case, it is a little bit tight. Why? We made it a little bit tight. So what is your frequency of interest? So your frequency of interest is FA, that is equal to 20 megahertz. What is the sampling frequency? Yeah, so you are going to use fs equal to 40 megahertz. So what is fs minus fa? So that is equal to 20 megahertz. Means all the frequencies after 20 megahertz will be folding back to your frequency of interest. So if you want to design a filter like this, then what you need is this is the amplitude, and then this is the frequency, and then this is the fs by 2, that is equal to 20 megahertz. Then your frequency of interest is 20 megahertz. So then what happens is you need a, and then your stop band is starting at 20. So your stop band is from here, it should start. So this is your stop band. Then you need a, isn't it? Yeah, because you need to design like that, isn't it? Your case, then what will you do? So that's the reason. Then here maybe you can say I will use not sampling, I can use maybe 80 megahertz. If it is 80 megahertz, you are okay, because if you got 80 megahertz, then what is your stop band? Where your stop band should be starting? 60. So now your stop band, then you can have, see, this is same. So now 60. Then what is happening is this is your 20 megahertz is here, 20 megahertz, and then your 60. See, now you can have 60. You got a bit more, at least stop band is starting here. So that is the reason, if you can increase the sampling frequency, you are getting a bit more space. But if you don't have a tight like this, then you can have something like this. So in your case, the design is tight. So then what I would recommend is your minus 3D. So your 3 dB point can be between 18 megahertz and 20 megahertz. So it could be maybe 18.5. You know what I meant? Your 3 dB. And then in the 3 dB, and then your pass band 3 dB. So that's the reason we already said only the 3 dB cutoff. We did not tell you the stop band. Because if we say stop band, you can't get it. So in your design, you don't have to worry, because you can have 18, maybe 18.5, and then let it come like this, depending upon your number of orders. But still then some high frequencies will be going in. You know what I meant? That is fine. But ideally, in your case, your stop band should start from 40. But that is not possible. So we want you to be thinking this. That's the reason we made that type design. Only some of you thought about it because it's a tight design. Now you know the pass band. In your case, people will ask, oh, DSO, you might be presenting in somewhere, some industry. Usually you go for jobs, they will ask some project or the subject you studied, and then some hardware subject if you are going to electronics company. Oh yeah, you designed the DSO. Then they will ask, what is the bandwidth you are looking at? Then you will say, oh, mine is 20 megahertz. Then they will ask, okay, sampling frequency 40. Then they will ask, where is your stop band? Then you will say that, oh, stop band equal to how much? 20. Then they will be asking, your bandwidth of interest 20, your stop band is 20. Have you designed actually a DSO? Then you can say that, yeah, that is a tight situation, the lecturer put it so that we will be understanding the effect of the sampling frequency. So for example, in our case, the bandwidth is equal to 20 megahertz and the sampling frequency equal to 40, and then we are in a tight situation. But then if you increase your FS to 80, then we can get 80 minus 20, like we getting some more, order. In order to understand that only, our lecturer made that one tight. Then in the really what you did is, you made your cutoff around 3 dB point, around 18.5 or 19, and then you got a kind of a slow transition. In your filter response, what is the stop band? You might be designed your filter. What is the stop band? So when you design it, you might be getting something like this. So you design. So I'm not showing you because it got some marks. So this is in your case, this is a 3 dB. So 3 dB you can have maybe 18.5 megahertz. And then depending upon that, depending upon your order, it will be coming like this. That is fine. And then this is a 20 megahertz, and then this is your sampling, Fs by 2. So Fs by 2 equal to Fb in your case. So this is a 20 megahertz, and then so your cutoff is somewhere here close to this one, and then this is your 20 megahertz. So this is your Fs by 2, but still you will have this part will be folding to this region. See, like this. Whatever the signal coming here, because this is your stop band may be far away, it will be folding into your DSO. So the DSO will not be a good one because you will be definitely suppressing, but that will be folding back. You know what I meant? So your DSO design is a bit tight. Then why we made a bit tight is because of this reason. So for each specification we thought a lot. So then now you know that, oh, I will be better off. You can say that with a high frequency ADC, so that I can design a better filter. You know what I meant? Now it is clear. Because now if you increase the sampling rate of your ADC, then you can design a much better filter. Because then your stop band is pushed away. So now your FB equal to Fs by 2, it is quite tight. So if you want to avoid this situation, then you can increase the sampling frequency of ADC, then you are getting a bit more space. So that is the reason we made that one. In order to understand that concept, we made it tight. But we know that in your DSO, you attenuate, but still some will be folding back. Yeah, so then DSO, please make sure that your 3 dB is between 18 and 20. You can't put it in the 15, 15, not a good design. But the stop band, we don't usually, how much it is coming, we don't usually evaluate it because it's depending upon your order. But in order to get a sharp stop band, don't go for a 10th order filter. Maybe 2nd order or maximum 4th order might be good. 2nd order might be ideal because of the space requirement. So if you are interested 4th order, you can go ahead, but 2nd order will be good. You can use one op amp and use the other op amp maybe for some new innovation if you want to do something. Having said that, some students designed the 4th order in the previous years. So they are getting a bit more sharper, though not much. Transition region. So anti-aliasing filters. So sampling has unwanted side effects of folding spurious signals into Nyquist bandwidth effectively, aliasing harmonics above the Nyquist frequency into a converter's baseband binary equivalence. Means we already studied the anti-aliasing means you are getting the high frequencies sampled as a low frequency and folding back. Then width of the transition band and required attenuation in the stop band determine the order of the anti-aliasing filter, which we already discussed. Larger transition regions greatly simplify the filter design as each increase in filter order requires additional circuitry. But the trade-off is that a greater amount of spectrum above the Nyquist frequency is allowed it to fold into the frequency of interest. Means we have to find out a trade-off between the sampling frequency and the number of poles. In reality, it is good practice for you to choose a sampling rate of 4 times higher than your frequency of interest. So if you are designing your DSO, then what is the sampling rate? 100 Hz, 100 megahertz is ideal. If you are making a very good DSO, you have to use an ADC with 100 megahertz, then that will be a very good design. You don't have much error. You know what I meant? With the 20 megahertz bandwidth, your sampling should be at least 4 times. Then you are sampling each cycle of waveform, each period 4 times. So in your DSO, your 20 megahertz, you are sampling with 40 megahertz. So you are kind of just meeting the Nyquist criteria. The final choice of sampling rate and filter transition band is heavily depend on your design requirements and signals you are converting. So then that is all about anti-aliasing filters. And then filters commonly used, already we discussed Butterworth, Bessel filters, then RC filters, maybe not a good idea to use these filters. And again the DSO one I think some of you got a little bit, because I got a couple of minutes more. Some of you I think got confused about what I said in the DSO. So I want to make sure that you understand. So in the DSO what is happening is, so I am going to ask you this question. So in the DSO, if your frequency of interest is 20 megahertz, your ADC, we said in the ADC you can go up to 60, but we said we will be using it to 40 megahertz clock. So your sampling is, we are going to connect 40 megahertz clock. So that is your sampling frequency. That is the 40 megahertz or 40 mega samples per second. So that is our CLK. So this clock is used for sampling the signals. And then so your Fs, which is equal to 40 megahertz. Then when you have Fa 20 megahertz, Fs equal to 40 megahertz, your Nyquist frequency Fn, which is equal to Fs by 2, which is equal to 20 megahertz. So when you are sampling below 20 megahertz, so that is your Nyquist will be sampled properly. Above 20 megahertz will be sampled wrongly and then fold back to the low frequency region which we studied. Now in this case, if you are designing a filter, your frequency of interest is Fa, that is equal to 20 megahertz. Then where is the stop band? So which frequency is a stop band? Means after that frequency everything will be folding into the frequency region. In your case, what is a stop band? Which is equal to fs minus fa, which is equal to 20 megahertz. See, then you should be stopping everything here as well. So because this is equal to fa, which is equal to stop band, fs minus fa, means then you should be having something like this ideal, which is not possible. In your case it is tight. You know this much is clear. Then you say that I can't design this filter. Very difficult if you have cutoff frequency here, 3 dB is 20 megahertz. Then in order to get rid of this issue, what you will do? Yeah. So if you increase the frequency, so then if I can use a ADC sampling frequency, instead of 40, I am going to use now fs equal to clock 80 megahertz. So if I use 80 megahertz, what is my stop band? So then the stop band will become fs minus fa, which is equal to 80 minus 20, how much? So now in my design, here now what happens is the same one, then now I got here fa. So here it is fa, that is equal to 20 megahertz, but now my stop band, that is fs minus fa, and then so that I may call it as f stop. So now my f stop, so my f stop is here, f stop, so that is equal to how much? 60 megahertz. So that now when you are designing, you can come to here, and then at least you can have a slope. See, you know what I meant? So then you this much transition you need infinite number of poles. But if you increase the sampling frequency, now at least you can design maybe a 10th order filter, and then you are getting a transition like this. See, this filter characteristics is more than sufficient. You know what I meant? But then in your case, what we did is we are not allowing you to increase the sampling frequency. Then it is very tight. If that is the requirement, because if you can increase the sampling frequency, you can find out, okay, you can increase this slope, you are getting now slope. Now your stop band is at 60 megahertz, so that you are getting this much space, so that this much transition region you can have. So maybe you can have a 10th order filter or something, so you can meet it. But in your case, we are not allowing this one. We are not allowing to connect a 80 megahertz clock. You have to connect a still 40 megahertz clock. And then it's a very tight design. So then what you can do is, if that is a requirement, then what you can do is you can just maybe a little bit move your cutoff frequency, this may be to 18.5 megahertz, and then that's the only way you can do. Then let it come depending upon your slope into like this. But then your stop frequency, this is your stop frequency, see, and then what in your DSO what will happen is, this is your stop frequency, that is equal to how much is stop? 20 megahertz. But then when you are having 3 dB point at around 18.5, then it is depending upon your filter order, it is coming, and then it is even going beyond the stop band. So then see, this is a stop band. So this much signal will be folding back into your frequency of interest in your DSO. You know what I meant? In your DSO, because of this reason, your some frequency of interest will be folding back into your frequency of interest. In your DSO is a tight design. You know what I meant? So you can take around 18.5, and then you can use maybe a second order. And then what happens is then you will be having this part will be aliasing to your frequency of interest. That's okay in your case. So it will happen here. But if you want to avoid this one, maybe you can use a high frequency sampling. Then what will happen is, see, this is a 60 megahertz is the stop band, and then this is your frequency of interest. Then what will happen? So this is your frequency of interest, and then this is a 60 megahertz. So all these things after coming 60 megahertz only, will be aliased, but then you are stopping at 60 megahertz, so you don't have much issue because your transition region is like this. So only this much will be reflected. See how much is coming here, that will be reflected to this frequency of interest. So you don't get up to here, so you will be getting only a small regions if you are using a high frequency. So if you use more sampling, then what will happen is you can extend this transition region. The slope of the transition region could be less if you extend the sampling rate. But here we haven't given that option for you, just because you want to learn, how to design in a tight scenario. Your sampling rate you are just meeting. So that is the reason you may have to put this 18.5, but then when you put 18.5, definitely your cutoff is much beyond your stop band. Your attenuation starts much beyond your stop band, which is okay in your case because you can't do anything else. But then within that one, how good you can design, that is the thing. I think hope it is clear, the filter design, everything. And if you got more questions, so I'll be having one more consultation maybe on Wednesday or Thursday, because it is difficult to find a time where you don't have workshop. Apart from Monday, you go to workshop. So I will be announcing one more consultation. So Bryce and I will be there. So if you got any other questions, you should come and see me this Wednesday or Thursday. I will announce it on LMS today. Another consultation before your submission, simulation report submission on Friday. So please submit your simulation report. And if you got any questions, I already discussed a sample of simulation report in my previous lectures. So please look into those report. And then there is a checklist. Have you seen on LMS there is a checklist? How many of you saw the checklist? Yeah. So there is a checklist. Please follow the checklist before submitting your simulation report. So we would recommend you to submit all the reports in time. The simulation report is on Friday, and then DSO, your final DSO PCB Gerber file also should be submitted within the deadline. Why? Because we have to send it out for fabrication. Then those guys have to fabricate and come back. So if you make like 1 or 2 days late, then that will definitely affect the fabrication time. So that is the reason we are strictly following the deadlines. Okay, I'll stop it here today.
Frequency of interest of DSO is 20 megahertz. But our signal is 10 megahertz.
Yeah, our frequency of interest is just 20.
Why is 20?
No, that's some design specification. Because in the DSO we decided 20.
Yeah.
Why? Because it is difficult to get an ADC more than 40 megahertz. You know what I mean? Yeah, we could make it 30 because we can use this one 60 megahertz. So then maybe we can make it 30, but then your frequency is increasing.
But our input signal is 10 megahertz.
No, your input signal should operate up to 20 megahertz.
But our tested
because 20 means that you are coming to the boundary. Because your cutoff will be 18.5.
So it's between 18 to 20.
Yes, it's a 3 dB point. After 18 and 20 so this will, we are putting this 20 megahertz because you are sampling with the 40. So that we want to make sure that nothing, not much is faulty to your frequency. So we put 20 as a specification based on the availability of ADC. Yeah, this could be in your case. In the real case, somebody will say 100 megahertz is the bandwidth. Then you should be having ideally what is the frequency. The Nyquist is 200, but then that is just bare minimum. Difficult. So ideally it should be 400 megahertz. Then only you can get a very good sampling. Yeah, so 20 megahertz we just made a number, 20 megahertz. Because of the ADC availability.
Yeah, so what's the frequency of the input signal?
It should be 0 to 20. Yeah, maximum 20. Yeah, we will not put 20 because your cutoff will be around 18.5. So I would say it should work up to maybe 18.
But why 15? 15 is not good.
No, 15 means you are losing, like it's not meeting the specification. Specification is, the specification we did not tell you 20 megahertz. specification. Why? Because you should be understanding from the sampling theorem, when your ADC got 80 mega samples per second, then what is the maximum bandwidth you can have? Because we did not specify 20 megahertz in your specification. What we said is you design anti-aliasing filter when you are using a 40 mega samples per second clock in the ADC. So when you have 40 mega samples per second clock, as per Nyquist theorem, you can't have more than 20 megahertz in your bandwidth. But then in your case, when you have 20 megahertz, then you can find out what is the stop band. Then your stop band and fs by 2, so it's very tight. Then you can make maybe 18.5, maybe. Not 15 is not good. Well, 15 you can put it, but then when you go to this maximum, because you just see the specification. What is the maximum possible bandwidth anti-aliasing, a good anti-aliasing filter? With 40 mega samples per second, you can design a 20 is the maximum you can design. So you design a maximum.
Like 20 megahertz is our interesting.
Yeah, interesting. Yeah, because beyond we can't go. Because when you got only 40 mega samples per second, 40 megahertz clock.
When you say 80.5 megahertz is just for the filter.
Yeah. I think that's fine.
Because if the filter is connected into the whole circuit and you measure the final output at the before the ADC, and you can see the cutoff will be moved like if we design 80.5, it will smaller than 80.5.
Yeah. It will be, when you measure the output, it should be around 18.5, 3 dB point.
Yeah.
Because if you put 20, what will happen is you are allowing a lot to go inside. Then aliasing will happen. Then the question is maybe then you will put 15. But then 15 or you can put 10. But then when you put 10 means that is very low.
Yeah.
So maybe you can put 18.5 or something like that.
19.3.
Then 9.3 also very good.
Very good. Very good.
This part is lost.
Yeah.
So this should be.
This should be 18, at least 18.
I mean, if it's 50.
18.5, yeah. 3 dB. 3 dB point should be 18.5.
And then when we calculate the power dissipation, what should our input voltage be? Because we need a table of power dissipation.
I will check it. I don't remember
It's like different input power have different input have different power, right?
Yeah, different voltages will be having different power. Yeah.
So what level of input we should have to? I'm talking about the power dissipation.
Yeah, because when you put different voltages, definitely the power will be different.
Yeah.
So how many voltages they are asking, like we are asking?
They didn't mention about it.
Yeah, they didn't.
Yeah, you can mention a couple of some voltages and then
So choose whatever we like.
Yeah. You put some voltages, but then you can't have above 5.5 volt.
Like
Within
just
that
choose
maybe you can
5
choose.
volts and
Yeah, a couple of them you can choose. Yeah.
so we have to list a table about every component's power or like the accumulative of the
I think it's accumulated power if I am correct.
accumulative of
Yeah. So have you got the specification?
at each part. Specification. Oh. Yeah.
Power dissipation table. A tabulated collection of DC bias and power dissipation simulation results taken at various important points throughout your front end. Net labeling should be. So after each important stage, like maybe after the clamping circuit, after the impedance matching, the RC, maybe after the buffer, something like that.
So we add a DC input and okay, measure the each point's accumulative power.
Yeah. So after after each after each section, after each block,
So the 18.5 megahertz common frequency is at the input of the ADC or the
input of the ADC.
output of the low pass filter.
No input because whenever we say bandwidth, we will measure at the input of ADC. Because whatever you get after the low pass filter, if you are not getting at the input of ADC, because that is the real one going into the ADC.
Yeah. Okay. Thank you.
Thank you.
You know what I meant? Otherwise, what will happen is you are getting a very good cutoff after your low pass filter. But then if it is not happening after the ADC, sorry, before the ADC, just before the ADC, you will be getting aliasing.
不是我一直一直都是 input
Yeah, so it says on the wrong parameter. The signal output is called ADC. It's like reversing because our amplifier is inverse.
Yeah, but then you may need to make it correct because you are